Hello. What's up, Sidetrack? Can y'all hear me fine? All right, good. Thank you for the thumbs up. Welcome to my talk, Recreating Retro Computer Art with JavaScript. My name is Sher Minn. It's a weird two-word first name, so it's Sher and Minn, Sher space Minn. It's a little bit of an unusual name. Downsides of that is that online forums really don't like it when you have a space in your name. So all of you here working on client-side validation, keep that in mind. On the bright side, though, my SEO is really great. If you look up my name, it's a first search result, and I didn't have to do anything. So life is good. I am from a small country in Southeast Asia called Malaysia. And yeah, we have actually another Malaysian in the house here, Hui Jing, that was on the stage at JSConf, so proud to represent my country. And I actually live in New York right now, where I initially moved to attend something called the Recurse Center. And it's a, woo, RC in the house, okay. So for those of you who may not know what the Recurse Center is, it is a programmer's retreat that's based in New York City. It's free, you can do 1 week, 6 weeks, or 12 weeks. And it's a really great place to rediscover the joy in programming. So if you want to take some time off to really learn something you've been meaning to learn, this is a great place to do it. And I always plug it because this is the reason why I'm giving this talk here today. Like everything they have provided me has enabled me to pursue creative programming. So creative programming, right? I like programming and I like art a lot. I learned how to draw before I learned how to code. And here are some of the pieces of work that I've made in the past year. And I really enjoy using programming to create code. And most recently, I've been really inspired by retro computer art. So what happened was that I discovered this magazine from 1976 to 1978. And it was edited by a computer artist, Grace C. Hartline, based in California in the United States. And this was the first ever computer magazine that was entirely dedicated to computer graphics and art. And as you can see here, the title, inexpensive graphics from the storage cathode ray tube really dates it. And I got these images from a website called the recodeproject.com. The site is no longer up, but it was a great resource to help you kind of just look through what was cutting-edge graphics back then. And as you can see, it's mostly black and white, text-based lines, geometric shapes. Today, we would call it minimalist or lo-fi. It's an aesthetic. And so it was really fun to look at and also to think about because most of the times, the work published is just the artwork itself. There wasn't a lot of algorithms. Most of the time, there'd be like some description of the technology used and maybe like some of the techniques, but no actual algorithms. So the whole purpose of the website that hosted this magazine, the archive for this magazine, were like, well, can we try and reverse engineer it? Can we look at a piece and try to figure out how it was made? And so that's exactly what I sort of fell into. And so this entire talk will be about the research that I did and also some of the attempts at recreating these works. So let's first talk about computer art. What is computer art? A lot of us have our own ideas of what computer art is. And it's probably right. In my definition, computer art is any art that in which computers play a role in the production or the display of the artwork. So today, that can include anything from, let's say, building an image using like Photoshop or Illustrator or 3D graphics, AR, VR, the latest, hottest thing, which is like, deep learning art, AI art. But we're not going to be talking about any of that today. We're going to be talking about the really, really early years of computer graphics. This was when computer graphics became accessible, and it'll be about how people took all those technologies and used it to make art. So the decade I'm focusing on is the 1950s to the 1970s, and this is really the crucial point where computer art was just becoming a thing. So everything's in black and white. So to talk about retro computer art, we first need to talk about what computers were like back then. The reason being that context really matters when you're talking about history. And if you understand the tools and the techniques that were available to people at the time, you can understand why certain pieces had a certain aesthetic or why was it done that way. And so it helps you appreciate a lot of the work a little bit better. here's a computer that was introduced in 1959, and this is the IBM 7090 data processing system. Not just computer, it's a data processing system, really fancy. It would take up an entire room. You can see like magnetic tape readers at the back, consoles and punch card readers. And it was introduced at a really cool price of $3 million. Back then, if you convert it to currency today, counting for inflation, it will be something like 19 million US dollars, which is really, really expensive. And so what this meant was that computers were really difficult to come by. The people who could afford it were people in universities, research labs, the military, government agencies, so they were very scarce of a resource. Can you imagine just calling IBM out and be like, I would like to buy a computer for $19 million, I'll write you a check, And most of the time, people wouldn't even interface with the computer. They would write programs for it using a punch card writer, which is like a typewriter, and you punch your code, and it will punch it into a punch card. You would take that stack of punch cards, hand it to a little man behind the door, and 5 minutes later, you will get your results back. And so, if you ever get impatient waiting for Webpack to build, think about this. So it's different time back then, right? Scarce resource takes a lot of time. And so they were mainly used for scientific and mathematical applications, like I said, mostly by scientists, mathematicians in research labs or universities. So I want to show you some examples of companies that really contributed to the field of computer graphics, the first being Boeing. And they actually coined the term computer graphics, and they were one of the very first few people to use computer graphics in their design work. So they would use this to design cockpits, to animate the different reaches of the limbs for a pilot in the cockpit. They use it for landing simulations. Here is the first airport that was simulated using computer graphics, the Seattle-Tacoma Airport in the United States. And there was also Bell Labs in New Jersey, also in the US, and they made one of the first ever computer-generated films. And I just want you to picture what that might look like, okay? And then I'm going to show it to you. So here it is. It is a simulation of a two-gyro gravity gradient attitude control system by E.E. Zagreb from 1963. And it's super cute. It's a satellite revolving around a planet. So as you can see, a lot of the early graphics, they were mostly designed to model or to maybe just demonstrate some diagrams. And so this really simple graphics of straight lines, geometric shapes, black and white, that was sufficient for their purposes. And so this was okay, this is wonderful. So you don't get things like fancy colors or gradients or anything like that. And yet, art happened anyway. People took the limited technology they had and did something really wonderful with it. So I'm going to talk about 3 different types of art. I just chose examples from each category. That's more. And I'll show you some oscilloscope art, some vector graphics, and some text-based art, and my attempts at recreating them. So let's start with oscilloscope art. So cathode ray oscilloscopes. If you've ever been in a lab, maybe in the school, you've played with one. And this is what an oscilloscope is, or this is what it looked like in the 1950s. It is a device that takes electrical signals and converts them into a visual over here. So here we have an example of a sine wave on an oscilloscope. So this is a little bit before the IBM 7090. And here on the left is a picture of Ben Lepofsky. He is credited to be one of the first few people who created electronic graphics. And so what I mean by that is that he would plot interesting patterns onto the oscilloscope, and he would then photograph them. And here are some of his works. And what's really interesting about them is that they look really ghostly, really kind of organic in a way, but you can sort of tell they have this mathematical quality to it. A few more. And around the same time, actually, in Europe, also, there was a movement getting started in computer art. Herbert W. Frank, he also created his own electronic artwork using oscilloscopes. Here's some of his work. So the interesting thing to note about this is that oscilloscopes don't have a screenshot button, right? There's no button you press screenshot, okay, this is going to come out. So in order to capture these images, what they would do is that they would set a camera in front of the screen and leave it on long exposure, and it captures the movement of the lines or graphics on the screen. And so what you're seeing here is not just a single snapshot, it is a culmination of events on the screen over time. And so here actually is an example of the same event, but 2 different phases of it. And I think it looks really beautiful, like a ghostly jellyfish. And here are more works by Leposky. And so it was kind of interesting to figure out, how were these made? I can, draw sine waves on a oscilloscope, but how do you get from that to that? And so there was a little bit of explanation in a magazine that featured Leposky's work called Recreational Mathematics. And in it, he explained that he used things like the sine wave, sawtooth wave, square wave, and Lissajous figures, which I'll talk a little bit about, in combination, so applying operations on them to create composite waves that had really interesting patterns. Here's an example of Frank's work that makes it really obvious that there is a bit of a sine wave thing going on over there. And I was like, how, okay, I get it, but what? How were these really made? And so I attempted to recreate it. So I'm going to show you a little demo here of recreation of Leposky's oscillons. That's what he would call his work. I'm going to use something called P5.js, which is a graphics drawing library based on processing. The processing language was designed to make drawing with code accessible for non-programmers. It's super great if you're interested in trying out graphical things. I highly recommend checking it out. It's got really great reference, really great documentation, and it has an online editor, which is really easy to use, so a good place to start. So let's jump to demo. All right, so in P5, you would usually have a global draw function that will get called to draw a frame of your animation or visual. And so in this, I'm just doing something really simple, just setting the center of the canvas as 0, 0, and drawing a tiny little circle here at 0, 0 with the width and height of 10 pixels. And that's not super interesting. What's more interesting is that you can animate things. So here, I'm adding a little counter and incrementing it at every frame that's being drawn, and using that value to position the x-coordinate of the little circle. All right, I can draw a line. So x increases, you'll keep on drawing to the right. But what's more interesting is that I can also draw a circle. And the formula for a circle is r sine theta, x equals to r sine theta, and y equals to r cos theta, where r is the radius of your circle. So great, now I've drawn a circle of circles. Circles are cool, but not super interesting. What's more interesting is that you can mess around with theta and can multiply it by 2 different fragments, and you get a pretzel. So this is an example of a Lissajous figure. It's when your sine and cos functions are at different phases, and so it creates really interesting loopy effects. All right. So what I can do now is that I can have the pretzel and then and draw an additional point, because pretzel is just 1 point. Draw another additional point that is the ellipse over here. And I can draw a line between those 2 points, and you get kind of that, but not quite still, because this overlaps and it keeps on getting brighter and brighter. So what you could do is that, you could fade out the lines as they're being drawn. And this, I imagine, would be what that might sort of look like on the oscilloscope screen, a closest approximation of it. So I have actually the code here in a P5 demo. I will send out a link to the slides on my Twitter after this, so you can play with it. And you can sort of mess around with some of the values and run it and see how that changes the movements or the effects. And it's kind of interesting because you never know what you're going to get. You just punch in stuff and it's oh, that looks good, or not. And then you just have to figure out what you're looking for. You can also add color here. Instead of drawing straight lines, I drew Bezier curves, but with a similar idea. And yeah, so that's it for oscilloscope art. Next, vector graphics. So vector graphics is a really special place in my heart. I really enjoy working with it. To understand why vector graphics are really important and why a lot of those pieces were mostly lines and geometric shapes, we need to understand what output devices were available at the time for people who worked with computers. So this was before laser printers. You can't really print a high-definition image really easily like we do now. In order to create really detailed images, people would use mechanical plotters. And you can think of a plotter as a drawing robot. It has a pen, and it can move on the Y or X axis and across the surface of a paper and draw on it. So this is a drum printer, so it moves the Y based on which is paper, and then X, which is the pen. And so the limitation with plotters is that all you have is literally a robot arm that draws lines. And so you had to describe your graphics in terms of vectors. So you had to provide it coordinates on which to move around. Can't do colors, can't do gradients, can't do like fancy things. And so a lot of the aesthetic back then had a lot to do with like lines, especially closely lines packed together to create certain interesting effects. And here's one that I saw a lot of. It was everywhere. And the basic idea is that you take a geometric shape, and then you nest it and rotate it a little bit, and you get this really cool swirly effect. And I was like, okay, interesting. Like it's just nested squares, whatever. And in fact, it was so popular that it was the aesthetic for cybernetic serendipity, which is the first ever computer exhibition that focused on computer art. And it was held in the Institute of Contemporary Arts in London. So it was a really big deal at the time. And so the fact that they chose this for the graphics was like, oh, okay, I guess must be really popular, or inspires some imagination. So a little side note about cybernetic serendipity. It was curated by a British-Polish woman, Jasia Reichhardt. And she's super amazing because she was one of the first few people who saw the value in this work and brought together all these artists and showcased them. And the name is a reference to the happy chance discoveries that you make with the computer. Because like sometimes you work with randomness and you don't really know what's going to come out, and sometimes it's something really beautiful. I saw this motif being used over and over again in really interesting ways. But I was like, okay, whatever, But later I found out this was actually a visualization to a calculus problem. And that kind of makes sense because a lot of early computer artists were people who access the computers, so scientists and mathematicians. And so the problem goes like this. Imagine 4 flies that sit on the corners of a card table, which is square, facing inward. They all simultaneously start walking at the same rate, each directing its motion steadily towards the fly on its right. And the task in calculus is to find the path of each. And I look at this now, and if I'm just like trying to solve it on its own, I'm like, okay, cool, whatever. And I don't really think much about it. It doesn't sound super interesting. But if you visualize it over here, with each color representing the path of a certain fly, it actually you get that swirly effect. And it gets really pretty when you draw lines between each of the different flies here. And I also added pretty gradients. Here are some videos just in case the demo didn't work. Gotta be prepared. And I found out that you could do this not just with 4, but you could do this with 3 flies or 5 or 6. And because I have a computer that runs really fast and I don't have to queue up for it, I can run it as many times as I want. And what I really like to do with this shape is to tile it. So if you put them all together, these are triangles. And what's really fun to see is that when you look at this, the first shape that you see is not a triangle. It's actually this like spade-like shape. And you don't expect that to come out of this. So kind of like that emergent property. Here's one with squares, and it's like a little mushroomy, like ram head shape. And it's really, really hypnotizing. So, all right. And now I'm going to tell you about text-based art. I know some of you are thinking, ASCII, right? But not really. I'll get into that. So to talk about text-based art, we first need to talk about what was it like outputting text. So there were CRT monitors, but most of the time when people wanted output, they would print it. So here is a line printer from the 60s, I believe. And it's called a line printer because it prints by lines. And it does that really fast because it has a fixed character set. You can only print certain characters. And it's like, just goes line by line. Super great for printing out text, right? And so people figured out ways to make creative works with this. For example, here, we have a couple of pieces of work by Frederick Hammersley from 1969. And you can tell that they were printed because of the perforated edges over here. I really like these two. And the interesting thing about this is that this was actually created with something called the Art1 programming language. And it was created by Catherine Nash and Richard H. Williams at the University of New Mexico. Nash was from the art department, and Williams was from the engineering department, and they collaborated to make this language. with the intention to teach students to make simple computer graphics. And it was notable for its simplicity and intended primarily as an introduction to the use of computers for those without any technological background. And I was like, that sounds familiar. That sounds like P5 and processing. That's really cool. So like Art1 was the original processing, or P5. This was from the 60s. And if you look at the documentation, it's like, well, it may look more complicated for Art1, but really it's the API is kind of the same thing. You pass in the center of the ellipse, and then you pass in the size of it. And it's like same thing, but the only difference is that Art1, you're going to punch it out on the card, and then do all that. But the P5 is just like type it in, it happens, magic. And another interesting thing that I noticed was that if you look at the detail of some of these pieces, you notice that the way that it creates its depth of texture is by overlapping characters. So remember how line printers have a fixed set of characters? So in order to get creative with like more textures and more effects, they would overlap two different characters together. So this piece is made out entirely of zeros, dots, dashes, and apostrophes. And I thought that was brilliant because you have a printer, you can print like over things. Let's do it. And I was really inspired by the fact that this was really art created by making the most out of the available technology back then, being really creative with what they had, instead of creating art in spite of it. So ASCII art, I guess, we still have this today, kind of. Only difference is that it's not really ASCII art, it's actually more like EBCDIC art, which stands for Extended Binary Coded Decimal Interchange Code, which was a character set supported by IBM at the time, and it was even more limited than ASCII. And so you can see here at the top of the card, the character set. It's a little hard to see, but it's not a lot of characters. So I was kind of curious about what was it like working in this language? This is really cool. Like original, Art1, what were some things what features did they have? What did they choose to include? So I did a little research, and it's surprisingly hard to find things written about Art1. The only place where I found anything significant was in Jasya Reichart's book. And in it, there was a little flowchart that described the workings of the language. And it had literally 7 drawing subroutines. You can draw lines, you can draw solid rectangles, you can draw open rectangles, triangles, ellipses, quadrants, and exponential curves, and that was it. I don't know why they had solid and open rectangles, but not solid open ellipse, I'm not sure. But I was like, oh, cool, this is really simple and really straightforward, and yet people can create interesting things out of it. So I was inspired to recreate this using JavaScript. So I have here the code, it's on GitHub, you can look at it. Still work in progress, so please don't judge. And so I was like, well, here's the thing. I don't have a printer, right? I'm not going to go out and buy a printer. So what's the closest thing that we have to a printer that's easily accessible? And I settled on the terminal, because both output tags, limited character set, wonderful, easy to use. And here's an example of a piece of work that I created using the same rules that were available in Art1. And here, these are all just made with triangles, but they have really interesting little 3D effect. You can do colors with terminals. Here's one that's actually inspired by the skirt that I'm wearing right now. So, and so you remember how I talked about how creative they got with overlapping characters? So here's the thing. Turns out, in a terminal, it's really hard to overlap characters if you're not using any external library like ncurses. So I was like, okay, what's the next best thing I got? Which is accents or diacritical marks. So if you see here for the S's, there's actually an accent at the top and an accent at the bottom. Same way here, this is the asterisk and then the accent with the box around it. And there are a lot of really interesting happy accidents, like the way that you color the background of the characters. Sometimes there's a little bit out of sync, but I kind of like that effect. So yeah, use what you have. I used Unicode diacritical marks. So not quite ASCII art, but Unicode art. And that was really fun to play with. And this really just skims the surface. There's way so much more history in computer graphics and computer art. In Europe alone, I actually tailored this talk for Europe because a lot of history came out of there. Germany gave us Friedenacke and George Nies, really prolific computer artists back in the 70s. And Hungary gave us Vera Molnar, who was making computer drawings before computers were a thing, and also when computers were a thing. And not to forget the entire New Tendencies movement in Zagreb, in what was once Yugoslavia, but today Croatia. And there's an 800-page book written on this, so if you want to look it up, the title's over here. This is an interesting movement because they celebrated like modular or procedural art even before computers were used for it. And as computer art became like more and more known, they also became a part of this movement. So yeah, before I end, I just want to talk a little bit about why. Why go through like all this research, like looking at things from 60 years ago? So a thing that I notice, especially in the web world, is that we are always looking at, what's new, what's shiny, what can I do next? And we don't take a lot of time to step back and to look at what has already been done. But it's important to understand that we didn't all get here just on our own. Like, we really, were built on we really stand on the shoulders of giants. And it's really important to know where you came from, because if you don't know what has already been done, you don't know, how to make something new. So, yeah, this has given me a lot of appreciation for the technology we have today. And of course, there is no shame in finding inspiration from the past. You can take what has already been done and make it your own, riff on it, learn from all those people who have put in all the work and creativity to get us where we are here today. And that's all I have for you. I have a blog. I write about this stuff if you're interested. But yeah, it was such a pleasure.